we can repeat the experiment as many times as we can wish. We can repeat the experiment as many times as we wish. So tossing a coin, outcomes are head and tail. That we know. That is the first one. Suppose we are tossing next outcome. We do not know whether it is head or tail. It may be head or tail. So we do not know the exact outcome. And we can repeat the experiment 10 times, 100 times, 1000 times, whatever. So if these three conditions satisfied, then it is called random experiment. So random experiment definition is clear? Hello?
Yes, sir.
Yes, sir.
Tossing a coin. Outcomes are head and tail. Rolling a dice. What are the outcomes? 1, 2, 3, 4, 5, 6. Okay. Generally, collection of all outcomes are called sample space. So in a random experiment, collection of all outcomes is called sample space. It is denoted by either S or omega. It is associated with random experiment. It is collection of all outcomes, and usually it is denoted by S or omega. This thing is called omega. So sample space is sample space. It is denoted by either S or this is omega. Sample space, that is collection of all outcomes. Okay, collection of all outcomes, that is a sample space. So it is associated with a random experiment, collection of all outcomes, and usually it is denoted by S or omega. Now event. What is event? Any subset of the sample space is called event. Okay, any subset of the sample space. What is event? Event is subset of sample space. Subset of sample space. So sample space and event definitions are clear? Hello?
Yes, sir.
Yes, sir.
Achha, is this handwriting okay? Means whatever PDF?
Yes, sir.
Yes, sir. बहुत अच्छी है.
Okay. Now event has two types of event. Simple event, compound event. So event has two types. Simple and compound. Simple event means exactly one outcome is there. Exactly one outcome. And compound means more than one outcome. Two or more. More than one outcome. See here it is written. An event is simple if it is consists of exactly one outcome. And it is compound event if it consists of more than one outcome. Then one example is written. Rolling a dice. What are the outcomes? 1, 2, 3, 4, 5, 6. So simple events are 1, 2, 3, 4, 5, 6. These are simple events. Getting even number. What are the even numbers? 2, 4, 6. That is a compound event because here three outcomes are there, more than one. Getting prime number. What are the prime numbers? 2, 3, 5. Tell me 1. 1 is prime number or not?
No, sir.
Why it is not? What is the definition of prime number? Your answer is correct. Can anyone tell what is the definition of prime number?
So it
is
has
divisible by itself
factor
and
as
one
one
only.
and the number itself.
Then 1 is divisible by 1 in itself. It will be greater than 1. In the prime number definition, see, p greater than 1 is prime number. It will, if only divisors are or it is divisible by p and itself. 1 and p. P is prime. P greater than 1 is prime. If p is divisible by 1 and itself. Here it is mentioned p greater than 1. That's why. Anyway, so we are getting even number, that is compound event, getting prime number, that is an compound event. Okay. So event and its classification clear? Hello.
Yes, sir.
Yes, sir.
Now we go to the classical definition of probability. That already we know, means whatever. See, many things. S be the sample space corresponding to random experiment. Suppose total number of all possible outcomes in S be n. So total number of outcomes is n. So that means we are assuming number of outcomes are finite. Means S contains finite number of elements. Each and every elements are equally likely. Means probability of the occurrence of each of the simple events are same. Tossing a coin. Two types of outcome, head and tail. Each of them have equal probability. Means that way. So equally likely. Means each of the simple event has same probability. And so occurrence probability is same. Rolling a dice 1, 2, 3, 4, 5, 6. For each of the occurrence, probability is 1 by 6. That thing is equally likely. Each and every events are equally likely. So S be the sample space. Suppose it has n number of elements, each are equally likely. That case, A be the any event and M be the number of outcomes in A. Outcome that is favorable to A. Then what is probability of event A? M by N. Number of points in A divided by number of points in S. This is called classical definition of probability. Here we are assuming total number of outcome is finite. But in general it may not be finite. That's why we require general definition of probability or axiomatic definition of probability. So whatever definition this is called classical definition of probability. Is this okay? Classical definition of probability?
Yes, sir.
Now probability of the sample space. See, number of P of S. Number of points in S divided by number of points in S. So from the definition, P of S is 1. What is P of phi? Empty event or null event? What is P of phi? P of phi is
0.
0. Basically, P of A is number of points in A divided by number of points in S. So P of phi null event, no element in A, that's why 0 by that thing will be 0. P of S, that is 1. Okay. Now some questions are done here. See. Two coins are tossed simultaneously. Find the probability of getting at least one head. So we will, by using classical definition, we will find it. Two coins are tossed simultaneously. So what are the outcomes? Sample space will be head head, head tail, tail head, tail tail. This is the sample space. Now find the probability of getting at least one head. So at least one head means either exactly one head or two head. So head head, head tail, tail head. So required even is clear. So P of A, 3 elements here, 4 elements, that is 3 by 4. Is this example okay?
Okay, sir.
Yes.
So, what is the probability that no head?
1/4.
1 by 4. No head means
Tail,
80.
tail.
Okay. In here, those things I am not writing here. Then, dice problem. In rolling a pair dice once, means what is the probability PA? What is the age the event? Obtaining 5 or a 6. Then B is the event even number. So rolling a paired dice. What is the sample space? S is the set 1, 2, 3, 4, 5, 6. A is the event obtaining 5 or 6. So A is 5, 6. P of A is 2 by 6. That is 1/3. Then B, even number. What are the even numbers? 2, 4, 6. Probability of B is 3 by 6. That is half. So these two examples clear by classical definition.
Yes, sir. Yes, sir.
Now we will go to some other definition, just like disjoint, say those type of things. So disjoint event or mutually exclusive events. So what is that? Basically, their intersection is empty. Okay. Mutually exclusive means their intersection is empty. Means they cannot happen together. So A and B are two events from sample spaces associated with some random experiment. A and B are said to be mutually exclusive if they cannot happen together. That means their intersection is empty. So if A intersection B equal to phi, then the event A and B are called mutually exclusive or disjoint events. See. So A and B mutually exclusive. A and B mutually exclusive means if they cannot happen together. If in mathematical notation A intersection B equal to phi or empty set. Now here rolling a dice. A is getting even number, B is getting odd number. Sample space AC is 1, 2, 3, 4, 5, 6. Getting even number 2, 4, 6. B getting odd number, so B is 1, 3, 5. A intersection B 5. Null set or empty set. A intersection B is empty. That's why A and B are mutually exclusive. Is this example okay? A and B are mutually exclusive.
Yes, sir.
Yes, sir.
Now suppose we are taking in this example another event getting prime number. So what are the prime numbers? 2, 3, 5. Then A is even number, B odd number, C prime number. So what is A intersection C? Here 2, 4, 6. Here 2, 3, 5. So 2. That means A and C are not mutually exclusive because their intersection is not empty. B intersection C. Here 1, 3, 5. Here 2, 3, 5. So intersection is 3, 5. So B and C are not mutually exclusive. Is this example okay? Mutually exclusive?
Yes, sir.
Then mutually exclusive. What is the meaning of that? their union will be the whole sample space. So exclusive means intersection empty. Exhaustive means it will cover the whole things. So here it is given, a collection of event is said to be exhaustive if in every performance of the corresponding random experiment at least one event belonging to the collection happens. So collection of sets will be given. Suppose A alpha is the collection of events. Then it is mutually exhaustive if its union equal to the whole sample space. Okay. A alpha belongs to lambda, that is indexing set. Means suppose you can take A1, A2, A3, A4 that way. Then this lambda will be 1, 2, 3, 4 that set. Each exhaustive if union of A alpha is the whole sample space. Okay. So exhaustive definition is okay? Hello?
Yes, sir. Yes, sir.
Collection of event exhaustive if their union is the whole sample space. Okay. Now one example is also given. Rolling a dice. So the collection of event A1, A2, A3 is exhaustive. A1 is 135, A2 is 2, A3 is 46. If you take A1 union A2 union A3, that will be the whole sample space. In fact, here A1, A2, A3 are mutually exclusive also, but we can take different things also. Means rolling a dice. Rolling a dice. Suppose we are taking, so what is the sample space? S is 1, 2, 3, 4, 5, 6. Suppose A1 is 1, 2. A2 is 2, 3, 5. A3 is 4, 6. So it is exhaustive or not? A1 union A2 union A3 is S. But A1 and A2 not exhaustive. Because 6 is missing that case. 4 and 6. A1 union A2 not equal
Yes.
to S. So A1 A2,
Yes, sir.
this collection not exhaustive. But here A1, A2, A3 exhaustive. Okay. So this example clear?
Yes, sir.
See, so in the classic now, again I am going back to the definition. Classical definition was P of A is M by N. M is number of points in S. Sorry, number of points in A divided by number of points in S. So that case we are already assuming S contains finite number of elements. 1 lakh, 1 crore, 5,000 that way. So S contains finite number of elements. But it not always happen. S contains finite number of elements. It may contains infinite number of elements. That case, what will be the probability of A? If S contains infinite number of elements, what is P of A? We cannot conclude.
Yes.
See, if that contains finite number of elements, A contains, then it will be 0. Because M is finite value, N is infinity. But not always that happen. Suppose from the set of integers, you are choosing even integers. What is the probability? Half. But infinity by infinity, that is not defined. So that's why we need general definition or axiomatic definition of probability. That was given by Komlogrov in 1933. Okay. So axiomatic or general definition of probability that was given by Komlogrov in 1933. So what is that? For that there are three conditions. Okay. Given a sample space S with each event A of S. So event means subset of S. With each event A of S, there is associated number P of A. So P of probability of the event A, that is basically a number. So that satisfies some properties. What are the properties? For any event, P of A is greater than equal to 0. For any event, it is greater than equal to 0. Okay. And for sample space, it is 1. So P of A, basically P of A is a number satisfying three properties. P of A is a let A be an event in sample spaces. A be an event and S is sample space. So PA is a number that satisfies three conditions. Satisfies for any event it will be greater than equal to 0. For any event this is greater than equal to 0. For any event A. Next, for sample space it will be 1. S is sample space, already it is written. Third one is if we have infinite collection of disjoint event. A1, A2, that way, in infinite collection of disjoint event. Okay. If then probability of their union means if we take probability of their union, that will be sum of their individual probability, summation pi over I. That is for disjoint events or mutually exclusive events. If these three properties satisfied, then it is called probability. Definition is okay?
Yes.
Three conditions for any event, it is greater than equal to 0. For sample space, it is 1. And A1, A2, A3, they are infinite collection of disjoint event. That case, probability of their union is equal to sum of their individual probabilities. If that type of condition satisfies, then PA is called probability of the event A. For any event, it is greater than equal to 0. For sample space, its value is 1. And if we have a disjoint collection of event A1, A2, A3, then probability of their union is equal to sum of their individual probability. So P of A1 union A2, A3, that way it will be PA1 plus PA2 plus PA3 and so on. That is summation I from 1 to infinity P of AI. This is called axiomatic or general definition of probability. You have to remember this one. Using these three properties, we will find we will find P of A union B, PA plus PB minus P of A intersection B. Then what is P of A complement? 1 minus P of A. Only using those definitions we will find all such results. Okay. So axiomatic definition clear?
Yes.
Yes, sir.
Okay. For any event it is greater than equal to 0. Sample space it is 1. Then if A1 union A2 infinite collection of disjoint events, then probability of their union equal to sum of their probabilities. Now we will prove probability of empty set. What is probability of empty set? What is P of phi?
0. 0.
How you prove this?
There is no event of fire.
No event, that's okay. Only these three things are in our hand. For any event it is greater than equal to 0. Sample space it is 1. An infinite collection of disjoint event, probability of their union is equal to sum of their probability. Basically these three results are in our hand. Not classical definition. Classical definition is m by n. But not always there may be finite number of elements. So how we will prove this thing using this? See. Achha, we know what is probability of the sample space?
1.
1. See. So using only those properties we will prove these things. What is S union phi?
S.
S. That is by set theory. Now if we take both side probability, it will be same. P of S union phi is P of S. Up to this line, okay?
Yes, sir.
Now what is P of S union
sir.
phi? We will apply
P of
axiom
S.
3. We will apply axiom 3. If A1, A2 they are infinite collection of disjoint event, then probability of their union equal to sum of their individual probabilities. So here S and phi are mutually exclusive. Sorry. Mutually exclusive. So what is P of S union phi by axiom 3? Probability of their union
1.
equal to sum of their probabilities. PS plus P of phi. Is this okay?
Yes, sir.
Suppose this is equation 1, this is equation 2. So from 1 and 2, what we will get? From 1 and 2, P of S equal to PS plus P phi. From
Yes, sir.
1 and 2, both are P of S union phi. So PS plus P phi equal to P of S. Then what is P of phi? P of S cancel. P of phi is 0. This is the actual proof. Proof is okay or any doubt?
No, sir.
Anyone has any difficulty tell? Just by logically we will do these things. Anyway, I will send you a notes on these things also. Is this okay? P of phi equal to 0. So here S union phi equal to S by set theory. Then we are taking, since both sides are same event, so their probability will be same. P of S union phi is P of S. Now LHS part, left hand side part, P of S union phi S and phi are mutually exclusive events, means intersection is empty. So by axiom 3, P of S union phi is Ps plus P phi. By axiom 3, I'll write here. By axiom 3. Then that way we are getting P of phi equal to 0. It is here, in this notes it is here. See the proof. S union phi is S from set theory. So P of S union phi is Ps. S and phi are mutually exclusive. So by axiom 3, P of S union phi is Ps plus P phi. That way we are getting P of phi equal to 0. Is that okay? P of phi is 0? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
What is P of A complement?
1 minus P of A.
P of A complement is 1 minus P of A. How you prove this? So not by classical definition. So we have to use by axiomatic definition. See, we are starting this way. What is A union A complement?
S.
Sample space.
Sample space. S. Then we are taking probability both sides. Probability of A union A complement, that is probability of S. What is probability of S?
1.
1. How you are getting? By axiom 2. See. Axiom 2 is P of S is 1. Just we will use only these three things. Then we will get all the things. By axiom, whatever notation is in these two. By axiom 2, it is 1. P of S is 1. Then A and P of A union A complement. What will be that left hand side? A and A
P
of A
complement.
plus P
Plus
of
P of A
A
complement.
complement.
See, A intersection A complement is phi.
0.
Not 0, it is phi. 0 is a number and phi is empty set. Okay. So A intersection A complement is phi. That is A and A complement are mutually exclusive. A and A complement are mutually exclusive. So by axiom 3, P of A union complement is PA plus P of A complement by axiom 3. That is 1. So this implies P of A complement is 1 minus probability of A. Is this okay?
Yes, sir.
See, P of A complement is 1 minus PA. A union A complement is S. So P of A union A complement is PS. S is the sample space. By axiom 2, P of S is 1. So it is 1. Then A and A complement are mutually exclusive. So P of A union A complement by axiom 3, P of A plus P of A complement, which is 1. So P of A complement is 1 minus P of A. Is this okay?
Yes, sir.
One more thing I will do. See, third property is probability always lies between 0 and 1. 0 less than equal to probability of A less than equal to 1. So how you prove this? First part is obvious, because by axiom 1, for any event it is greater than 0. By axiom 1, P of A greater than equal to 0. So first part is done. Then we have to show P of A less than equal to 1. How you can show that P of A less than equal to 1? So first part is okay. By axiom 1, P of A greater than equal to 0. Is this part okay? Hello?
Yes, sir.
Now
Yes, sir.
remaining thing is we have to prove P of A less than equal to 1. So how you can show P of A less than equal to 1? See, we cannot see A subset of A that way. So P of A less than equal to P of A that we cannot apply. Only things whatever we have learned till now. See, for any event probability is greater than equal to 0. So A complement is also an event. For that it also true. By axiom 1. P of A complement also greater than equal to 0. This is true for any event. A complement is also an event. For that it is also true. This line clear?
Yes, sir.
Yes, sir.
Now just now we have proved P of A complement is 1 minus PA. This gives 1 minus PA greater than equal to 0. That implies P of A less than equal to 1. So that's why 0 less than equal to P of A less than equal to 1. This is the proof. For any event, probability greater than 0. So P of A greater than equal to 0. For remaining part, P of A less than equal to 1. A complement is also an event. For that also axiom 1 true. That's why P of A complement greater than equal to 0. P of A complement is 1 minus PA. We just now we have proved. So 1 minus P of A greater than equal to 0. That is P of A less than equal to 1. Okay, that's why 0 less than equal to PA less than equal to 1. Is this okay?
Yes, sir.
See.
Yes, sir.
P of A greater than equal to 0 also by axiom 1, P of A complement greater than equal to 0. For any event it is true, so that way it is fine. Then some more proofs are there. Anyway, remaining thing we will do in the next class. So up to this it is okay?
Yes, sir.
Any suggestion or anything about way of teaching?
Sir, please share this.
No, sir.
Huh? Way of teaching is okay or not?
Yes, sir.
Yes, sir. It is okay.
Yes, sir.
See, if you face any difficulty, you tell me. Anyway, I will share these notes in Google Classroom, okay?
Okay, sir. Thank you.
Okay, then wait, I will take attendance.
Okay, sir.
But these proofs will come, sir.
These proofs may come.
Okay, sir.